minimally or moderately rough implants in the presence of supportive periodontal therapy. But the commercial companies are still working on different surfaces, and we are no longer dealing with microns. We are dealing with much smaller components, and the aim is to load the implant as fast as possible. So, smaller particles, and we are in the nano business. Nanometer structures are quite common today, nanometer coats of different kinds, bioactive surfaces, hydrophilicity or hydrophobic implants, and biofilms. To start with the nanostructure, we have some evidence, of course, of the design, which you could regard as a millimeter roughness. We have some knowledge about the micrometer roughness, which I've tried to give some results upon. But we also think that nanostructure may have an importance due to they may attract some certain proteins that may be important for the future healing. So maybe this nanostructure could have a clinical impact too. First of all, what is a nanoparticle? According to the definition Webster published 2005, it's a grain size between 1 and 100 nanometers. And the evaluation techniques to measure such a small, tiny structures are really small. Either we can use an atomic force microscopy, or we can use a scanning electron microscopy. But then, to be able to see any nanoparticles, we need to have a magnification of at least 60,000 times, and preferably use an in-lens scanning electron microscopy. From the biological point of view, we are in the range of a water molecule. So it is really small and tiny structures we are dealing with our modern implants. In vitro studies have demonstrated some advantages with the nanostructures, such as enhanced osteoblast density and osteoblast adhesion and proliferation. There also exists some in vivo investigation. Luis Miralles presented his thesis, and I think he was really one of the very first ones who were able to investigate nanostructures in vivo. He used a very smooth surface to get rid of all influence of microstructures. He coated one of the implants with hydroxyapatite 20 nanometer structures. And from this profile, where you see on the bottom of the topographical images, you clearly can see the difference in density and also, of course, in surface enlargement for these surfaces. And he could conclude that the nano-coated surfaces had a significantly improved bone-to-implant contact. So, in summary of his thesis, which consisted of 5 different publications, he found no evidence for hydroxyapatite being bioactive, but strong indications that the nanostructures are of importance for the early bone healing in vivo experiments. Bioactive surfaces. It is sometimes very difficult to separate nanostructures with bioactivity. But according to the very first definition of chemical bonding and bioactivity, they should provide with a very strong and very defined bonding between the implant surface and the bone itself. Today, this definition has slightly changed and are today more related to a certain material that attracts certain proteins that are important for the bone healing. There are a number of surfaces claimed to have a particular interest in bioactivity, such as the anodization, such as sodium hydroxy coated and treated, heat-treated implants, and also some ion-treated implants, such as fluorides. In experimental surfaces, there has been also demonstrated that fluoride ion may be of importance, but also in different in vivo characterization and surfaces. We did like to design a study, and we therefore used blasted implant as a control. We then, part of them treated with fluoride, etched it within hydrofluoric acid, and another group we coated with nano-hydroxyapatite particles. They were left in rabbit tibia for 4 weeks, and we did find a significant difference between the untreated and the additional fluoride-coated or hydroxyapatite-coated implants. But no difference between the fluoride and the hydroxyapatite. So the chemical-treated implants demonstrate the higher removal torque as the fluoride. So is there similar reaction between these two methods to improve osseointegration? Or have they the same similar bioactivity? Or actually, is this all about the nanometer effect? Because that is one of the problems. When you change something, you normally also change some other surface property. To the left side, you see a blasted surface, and then it's a blasted surface plus a fluoride etching. That is, all of a sudden, some of the outermost titanium oxide layer has reorganized into nanoparticles. And to be able to evaluate all these new small particles, maybe our old evaluation techniques are a bit too coarse. So therefore, new evaluation techniques such as micro-CT may be of importance. Another way to try to evaluate these small features are to analyze the gene expression of the cells that come in contact to these surfaces. We have tried to evaluate hydroxyapatite on the surface. We have extracted them. We have extracted them at a time of implant retrieval. We analyzed the insertion torque, no difference between the surfaces. Found some differences in removal torque, with an advantage for the nanostructure surfaces after 2 weeks, no difference after 4 weeks. But we found a big difference in gene expression in terms of both early bone markers as well as the very early healing period, such as the alkaline phosphatase. So it was evidence that we have some influence on the genes for enhanced osseointegration. And also that this may be a sensitive method to evaluate nanostructures. But as for the micro roughness, there may be some negative effects with nanostructures. Nanotechnology are today used everywhere. We have it in the pharmaceutical industry, we have it in our cosmetics, and we have it in our foods. So some concern has been raised. What happens if all these nanoparticles enters our cells? Will they change? So we designed a study to see what will happen to a nanocoat on a rat surface. We characterize it. We know that we had a nanocoat. We marked the calcium with calcium-45, which is a radioactive substance. It's very high activity. The red color indicates a very high activity. It decreased quite rapidly. After 4 weeks, it has decreased considerably. And after 8 weeks, there were no more activity around the implants. We also analyzed the wooden shavings where the rats lived on, and we found the largest amount of activity after 2 weeks. In the blood, it was a constant decrease of activity, and we found some high amounts of calcium 45 in the liver, but nothing in the brain, nothing in the thymus, and nothing in the kidneys. So, at least from this study, it seems that the particles are released from the study, but they leave the body in a quite natural manner. Much effort has been spent on implant surfaces. Not so much has been spent on the optimal surface for an abutment or the prosthetic supraconstruction. And threshold value has been mentioned to be about 0.2, 0.3 for plaque accumulation, but if we could have any benefits from a nanostructure on the implants is yet not known. We investigated the surface with respect to some surfaces investigated by a Finnish group who has found that nanocoats would enhance soft tissue healing. Therefore, we used microimplants, inserted them in humans, in 15 patients. We evaluated the part that penetrated the mucosa and were not so much interested in the bone. We evaluated semi-thin sections to be able to characterize the different cells. And then we also did very thin sections to be able to see whether or not we could find hemidesmosomes that would be a proof for a direct contact between the surface and the soft tissue. In our results, there were no big difference actually between the test and control, except for the clinical appearance, where there seems to be a huge difference between the nanostructures and the non-coated structures. The test implants showed a much more healthy appearance compared to the tests. Hydrophobicity, or the wettability of the surface, is another topic quite popular today. It deals with the contact angle, and people are interested in particularly if the suprahydrophilicity will have an impact. That is a contact angle less than 0.5 degrees. Titanium is normally hydrophilic, but what will happen if you increase the wettability even further? Some studies have shown that this is of importance, and our own studies could confirm that UV seems also to enhance the early bone healing, as evaluated with micro-CT and gene expression. But again, is this really an effect of the wettability, or is it again of the nanostructures? On the left side, it's a blasted and etched implant, and here is after a hydrophilic or improvement or extremely clean. Again, you will receive some nanoparticles with this additional treatment. Why, we don't know, but for sure this is particles, a reorganization of the outermost surface layer. Finally, we have biofilms. Some coatings may be of importance. We know that certain proteins are of more interest for bone healing and soft tissue healing. Laminin could be one example. We started to test it in a simulated body fluid, which is the first step to evaluate the bioactivity. We could see that it was hydroxyapatite and not any other type of calcium phosphate. We could also see that different surfaces seems to accumulate or stimulate this calcium phosphate precipitation. And there seems to be a big difference between bioactive laminin-coated implants compared to blasted non-coated implants. So laminin is another way to change the surface topography that may be of importance. But again, for all these new surfaces, we don't have any clinical evidence that it will improve our clinical treatment. But to summarize my presentation is that implants of today are developed from the minimally rough status, the turned surface, to moderately rough surfaces. They today have nanometer structures on the surface. And very often, they also have changed the chemistry. But which of these surfaces are the optimal still remains to be investigation. So I guess that the hunt for the optimal surface will continue. And with that image, I would like to thank you for your very kind attention, and I would like to thank my group for their work. Thank you very much.
Thank you, Mr. Chairman. Dear colleagues, ladies and gentlemen, good afternoon. First of all, I would like to thank the organizing committee for this invitation. Thank you. Thank you, Professor Park. The title of my presentation is Implant Surfaces and Implant Connections, Past, Present, and Future. Many years ago, Confucius, before Christ wrote, study the past if you would find the future, and I add, and the present. 50 years ago, the pioneers of the implantology practiced the immediate loading and intraoral welding using one-piece implants with a tapered neck, but with poor scientific evidence. And today we follow the same concept, but with much more scientific evidence. And we aim to maintain the peri-implant tissue for a long-term period. The biological tissue preservation concept involved the following point: to position the implant on the crestal, to use the implant with the shoulder and surface microstructured, to use a platinum switching concept, tapered connections, the SLI design, no abutment rotation and without micro movements, without micro gap that must be less than 10 microns, and no bacterial infiltration, ne statically, ne dynamically. In this presentation, there are two main topics: the implant surfaces and the implant connection. The surfaces promote and accelerate cell adhesion, spreading and proliferation. The connection maintain the bone level for a long time period. Promote and maintain are the key factors for a long-term success. In the last 7 years, several articles about implant surfaces have been published. And the article review indicated that implant research should still fully understand the neurophysiologic, the vascular, hormonal, immunological, and genetics up and down regulation mechanisms that underlie the osseointegration, the role of the surface roughness, microtopography, and chemistry on cell adhesion, spreading, migration, proliferation, and differentiation. We also know from the literature that the interaction between the cells and the implant surface is determined by the surface structure or surface composition, but not by the bulk material. The interaction between the cells and the surface happened in the first 5 nanometers of the implant surface. And we know also that the treatment used to obtain a change on surface topography is reflected often in the surface chemistry of the implant and could affect the cell response. In this article published in the journal Oromaxillofacial Implant from Dr. Essa Cassinelli and Dr. Marco Morra from Italy, Villafranca, they analyzed 34 implant systems chemically using the XPS analysis to find which elements are present on the implant surface. And they found that in addition to the oxygen and to the titanium present in the percentage ranging from 1% to 18%, they found other elements residuate from cleaning, machining processes, sandblasting processes, etching processes. Here are listed the processes of surface treatment of implants in the past and the present and the immediate future. Machining and position processes such as plasma spray, TPS, and hydroxyapatite, sandblasting, acid-acid, galvanic oxidizing, anodizing, hydrofluorizing, hydroxylation, laser texturing, nano apposition, composite surfaces, surfaces modified by bone morphogenetic proteins, nanotechnologies, and surfaces gene modified. First of all, we have to know how the surface appear. And in this picture, you can see a typical machine surface. This picture illustrates a sandblasted surface. You can see the presence of the particle of alumina residuated from processes of sandblasting. This is a typical acid-etched surface after sandblasting. Double acid-etched surface, full acid-etched surface. This is the RBM surface. This is a sandblasted surface, but with using a removable blasting media with the calcium phosphate particle and then cleaned with acid. Is a particularly clean surface. Sorry. This picture shows the SLA acid surface. In this picture, you can see a residuate of alumina particle on the surface. But we know from the literature that the presence of alumina does not affect the cell behavior, the biological cell behavior during the proliferation, the growth on the surface. This is a surface anodized, oxidized, nanostructure. This is the X-speed surface. The X-speed surface is first sandblasted and then subjected to an anodization process in a low voltage calcium ion solution that leaves a thick of calcium ions ranging from 500 and 700 nanometers. In this study, it has been investigated if the surface treatment affects the cell biological activity and in which way, with the limitation of an in vitro study, obviously. We analyzed two kinds of surfaces in the same implant system. The only variable was the surface. We included in the research design morphological analysis by SEM, chemical analysis, ADX and XPS, the stereosem analysis to evaluate in three-dimensional way the roughness of the surface, cell adhesion, migration, and all the biological part of the study, with, at the end, the ILP, or alkaline phosphatase activity, to evaluate the potential of differentiation of the surface. Two surfaces analyzed, sandblasted and acid-etched in high-temperature process. This is the result of the chemical analysis by X-ray photoelectron spectroscopy. And you can see the difference between the two surfaces. The sandblasted presents a high percentage of elements residuated from sandblasting processes, like silicium, like calcium, like alumina. The acid-etched surface is more clean and presents a higher percentage of titanium, quite 20%, and a high percentage of oxygen on the surface. In this picture, you can see the results of the analysis of the macro roughness using the stereosem. This is a 3D analysis to evaluate the three-dimensional degree of roughness of the surface. And here you can see the difference between the two parameters that we use, the peak-to-valley distance and the peak-to-peak distance. The RA value, the two-dimensional roughness analysis, is quite the same between the two surfaces. The difference is in the quality of roughness, measuring the distance, a peak and another peak, the density of porosity of the surface, and measure the depth of each pore. The result of this first part of the study is that the self-roughness microdesign and surface chemical composition did not play a role into in vitro cell differentiation. We found a more rapid increase in cell proliferation, but we didn't find any difference in biological activity studied by ILP analysis. So, in the other study, we wanted to analyze if the implant macrostructure can affect the surface treatment and consequently the microphotography and the chemical composition. The aim of the study was to investigate which biological cell activity is influenced by the fixture macrostructure, the surface microtopography, roughness, pore morphology and dimension, and chemical composition. For this study, we use 26 EZ plus internal implants from Megagen and 26 any-ridge implants and 24 discs treated with RBM, sandblasted, typical sandblasted surface, and X-speed, sandblasted, and then anodized with a calcium ion solution. The study protocol involved a comparative study design. We analyzed and we compared the same surface with two macro designs and the same macro design with two surfaces. This is the research design, involved the morphological analysis, the SEM analysis, scanning electron microscope using the backscatter electrons techniques, the chemical analysis, the roughness stereosem analysis, and the cell adhesion proliferation, and the gene expression by real-time reverse transcription. In this picture, I would like to show you the difference when you acquire an imaging with using a normal signal versus a backscattered electron signal. The backscattered electron signal allows us to individuate the presence of macrocontamination on the surface of the implant. Same image acquired in two different ways. This is the RBM surface at various magnification. It is a typical sandblasted surface with the presence, of macropore on the surface. The surface is very clean because was cleaned by an acid solution after blasting. This is the X-speed surface on the same fixture. Something changed. You have the same image of the previous, but there is another structure present around in the deeper part of the macropore. This is the sandblasted surface on the any-ridge implant. And here you can see the X-speed surface on any-ridge implant. The chemical analysis revealed the presence of carbonium, and this peak was very high in the X-field implant treated with RBM surface. You can note also the presence of the calcium on the surface. And this is the result of the chemical analysis of an ridge implant with RBM and X-speed surface. Here you can see the carbonium. The carbonium is an organic, carbonium presence indicate an organical contamination, maybe during handling processes, for example. And also a peak of calcium in the X-speed surface. In this table are summarized the results of the chemical analysis, and you can see that the surface chemical composition of RBM surface on a zeta plus implant and any-ridge implant was quite similar. But we found difference in chemical composition between the X-speed surface on a zeta plus implant and the X-speed surface on any-ridge implant. The fixture macrostructure may have affected the X-speed surface treatment. The calcium is detectable also using the ADX analysis. The difference between the ADX analysis and XPS analysis is that with ADX analysis you can check, you can control the 5 micrometers of the surface of the implants. With XPS analysis you can check, you can control, you can investigate the first 5 nanometers of implants. These are the results, these pictures show the results of three-dimensional analysis of surface, roughness surface. The stereosem analysis is an analysis that uses a sequence of images that are rebuilt, reconstructed by a software, and then indicate a three-dimensional roughness of the surface, a three-dimensional map of the surface. What we measure? In particular, the RSM value, the peak-to-peak distance. We measure the distance between the peak of the pore present in the surface and the RZ value that indicates the depth of the pore. In this table I showed the results. We didn't find any difference in roughness between the two surfaces. So what's happened from a biological point of view? In this picture, you can see the cell proliferation. We use osteoblast-like cells derived from osteosarcoma, human osteosarcoma, is an immortalized line cell that we use, we can use it many, many times to have a repeatability of our experiments. This is the RBM surface on EZ Plus implant at 4 and 24 hours. You can see the globular aspect of the osteoblast in the first hour of growth, and after 24 hours, you can see a multi-layered presence of osteoblast with the cell body flattened on the surface of the implant. This image is from any ridge with RBM's surface. EZ Plus with X-speed surface. Seems that the cells, the osteoblast cells, proliferate more rapidly. And in this image, obtained using a backscattered electron signal, you can see that the cell proliferation at 4 hours and 24 hours is more rapid compared to the proliferation on the RBM surface. We performed also another study, another analysis with immunofluorescence. With immunofluorescence, you can see in better way the amount of cell proliferation. Look at the difference. This is the same image obtained from a scanning electron microscope and from immunofluorescence analysis. You can see the green points, the green lights are the cell body, and you can see that are more and more than appeared in the picture on the right. The immunofluorescence analysis confirmed the increase in proliferation on the X-speed surface compared to the RBM surface, with nuclear staining analysis and with staining of cell bodies. The part one of the results. The X-speed and RBM surfaces have different chemical composition. The X-speed surfaces of EZ Plus and any ridge show different chemical composition. Their macrostructure may have affected the surface treatment. The X-speed and RBM surface have similar values of roughness. Both surfaces are sandblasted, and the nanometric calcium ion layer on the X-speed surface does not modify the roughness. Cells on the X-speed surface have a greater increase in proliferation and spread more rapidly. We continue the study because we would like to investigate if some gene involved in bone formation, cell differentiation, healing, or bone resorption were involved in this process, and what changed using another type of surface. These are the result of analysis, gene expression analysis of the any-ridge implant. And in brown, you can see the RBM surface, and in blue, the X-speed surface at 24 hours, 72 hours, and 8 days. In this picture, you can see the same results from a Zeta Plus implant. In green, the RBM surface, and in red, the X-speed surface response. Data from any ridge PCR analysis show that osteoblast-like cells grown in 24 hours on the X-speed surface have an overexpression of some genes that regulate the processes of bone regeneration compared to those grown on the RBM surface. After 72 hours, gene expression is similar between the two surfaces. After 8 days, gene expression is much more evident on the RBM surface, indicating that the osteogenic processes are faster on the X-speed surface. Data from a Zeta Plus PCR analysis show that osteoblastic cells grown in 24 hours, 72 hours, and 8 days on the X-speed and RBM surfaces have similar gene expression. Conclusion: with the limitation with all in vitro study, it can assume that differences in gene expression, even within the same surface treatment, may be due to macrostructure characteristics, fixture design, and geometry as follows, affecting the surface treatment and consequently the surface chemical composition. Next steps. If you saw the lecture of Professor Estaben, you know that the future are the bioadhesive surfaces, the tissue engineering using stem cells, and osseointegration and bone regeneration using the gene therapy. We study in this sense with the differentiation center directed by Professor Ranieri Canceda in Genova, and we studied the problem using a scaffold on model animals and using the micro-CT with the synchrotron Eric source to have tridimensional result of the interface between bone and material regenerated on the surface of the implant. The second topic is the connection. The connection should be classified in external connection and internal connection. External hexagon, internal hexagon, octagonal, 3 multilobated, screw tapered with and without index, Morse tapered, and the interface classification is flat to flat, a tube in tube. We have to distinguish the classification of the connection from the classification of the interface. The interface are 2, flat to flat, horizontal interface with and without platon switching, a tube in tube, a vertical interface with always the platon switching concept. In literature, you can find many articles about platon switching concept. In the first year, the article was very, very few, but in the last 2 or 3 years, they increase in number. Today are 77 reported by PubMed. And the first one was from Dr. Lazzara, published in the International Journal Periodontics Restorative Dentistry. The platon switching is a purely mechanical and geometrical concept with biological implication, that it's simply to restrict the ICT area, tissue connective infiltrated area, more medialization, away from the bone implant interface. This is the platon switching concept. We can measure the platon switching, yes. using scanning electron microscope. For example, the any-ridge implant abutment connection has got a platon switching about 500 microns. The EZ plus internal implant abutment has a deep platon switching, about 1,000 microns. But the question is, is the platon switching sufficient enough to maintain the bone and soft tissue stability for the long-term period? In this paper published by Becker and Schwartz, they analyzed the stability of crestal bone level at platon switch non-submerged titanium implants. They concluded that the bone remodeling was minimal in both groups with and without platon switching, and that platon switching may not be of crucial importance for maintenance or crestal bone level. The platon switching is not enough. We need other parameters, and they are tapered connection, S-line design, the absence of microgap, less of 10 microns, no bacteria infiltration, neither statics, neither dynamic, no abutment rotation and micromovement, and the undercrestal position on the fixture. The tapered connection are classified in connection by screw tapered connection, such as Astra, Ankylos Plus, EZ Plus internal, any-ridge, and connection by friction grip, or Morse tapered connection, such as bicon or hexagon. There are many factors from a mechanical point of view that determine the tapered connection. The advantages are mechanical, functional, biological, and aesthetic. Mechanical advantages because we know that the conical connection, the tapered connection, has a shock absorption potential and allows the distribution of the stress along the connection. The functional advantages, no rotation. The conical connection can't rotate. There is not static infiltration. The biological advantages, we have a reduction in the marginal bone loss and an increase in connective tissue depth. A three-dimensional osseointegration and minimally invasive reopening. Aesthetic advantages are transmucosal seal, choice of the abutment regardless of the fixture diameter, one-stage surgery with transgingival healing, and the occlusal design that could be respected. This is an independent study from Boston University, Dr. Botskaya and Muftu. They analyze from a mechanical point of view the characteristic of tapered connections. They concluded that the Morse tapered connection, the screw tapered connection, show a more homogeneous distribution of bone stress, while in other systems was mainly concentrated in the cortical area. The any-ridge implant connection is the 5.1 degree, from a zeta plus internal ranging from 12 to 18 in our analysis. Dr. De Gidi, in this paper, studied the behavior of the bone and soft tissue around the implants with platon switching and the position undercrestally. They put the fixture in human, 2 millimeters below the alveolar crest level, and they found, after 4 weeks of healing, that the bone was present 2 millimeters above the level of the implant shoulder. No resorption of the coronal bone was present. No infrabony pockets were present. At the level of the shoulder of the implant, it was possible to observe the presence of dense connective tissue with only a few scattered inflammatory cells. Newly formed bone was found in direct contact with the implant surface. And it's very important, when the fixture with a tapered connection is inserted below the alveolar crest and the healing screw or the abutment is positioned, we obtain a chamber according to De Gidi. The floor is given, the floor of this chamber is given by the implant shoulder. The lateral walls are given by bone above the shoulder and connective tissue, and the roof of this chamber is given by the abutment crown system. We know from the literature that connective tissue could organize itself around the abutment also after many years of loading. This image, from a clinical point of view, is the image that we would like to see every day. This is the chamber. And this transmucosal connective tissue seal, it's so important that it would be better don't touch it at all after healing. Dr. De Gidi, in this publication, published on Clinical Oral Implant Research, has written that the non-removal on an abutment placed at the time of surgery results in a statistically significant reduction of the horizontal bone remodeling around the immediately restored subcrestally placed tapered implant in case of partial posterior mandibular edentulism. Another factor to obtain the biological tissue preservation and to maintain the biological tissue preservation is the absence of microgap that should be less than 10 micron to avoid the bacterial infiltration. In this paper, in this work, Dr. Dietmar Weng analyzed the affected microgap positioned at the level of the crest and under the level of the crest. He used two typical connections, tapered connection, tube-in-tube, vertical interface, and a typical flat-to-flat interface, horizontal interface connection. And he put the implant at the level of the crest and under the level of the alveolar crest. And after the healing period, he found that the bone stayed at the same level of the surgery, but when used a connection flat to flat, the bone grow down. And statistically. The microgap of the any-ridge implant abutment is less than 1 micron. We found a gap of 442.8 nanometers. The abutment with flat-to-flat connection can rotate and can move. In this video, you can see the movement and the opening of a flat-to-flat connection under an axial load of 100 Newton. You can see again here. Okay. This is a typical conical screw-tapered connection. No movement. No opening of the margin. There is a tube-in-tube. There is a vertical interface, not an horizontal interface. In this case, we can avoid the bacterial infiltration. And the last point is the undercrestal positioning. If you don't have these characteristics of an implant system, you can't put the implant undercrestally. We want to be sure that all the characteristics of our system allows us to maintain the bone level. Stig Hansson, in this paper, studied the problem using the finite element analysis, the problem of the positioning of the implant, and he concluded that the neck of the implant should be placed at the height of bone crest or just below. Crestal bone is stimulated by loading forces in accordance with the Legge di Wolf, decreasing the amount of resorption. If the interface is located 2 millimeters coronally, stress increases. If you use a tapered connection, you have to put the implant at the same level of the bone crest or under the level of the bone crest. If you put the implant over the bone crest, after 2 millimeters, the stress increases. And you lost the mechanical properties and the mechanical advantages of tapered connection. Under crest positioning and the maintaining of the bone level. Another case. This is the chamber. If you use an implant system with a conical connection, with a tapered connection, you also put the implants with the inter-implant distance of 2 millimeters. And you will not lose the bone between the implants. Because in this area, you don't have micro-movement. In this area, you don't have micro-infiltration. In this area, you have a mechanical tapered connection that distributes the stress along the connection along the implants and not on the crest, or the bone crest. After 2 years, you can maintain the bone level, the same bone level that you had when you finish the work. And the tissue are stable, and the patient is happy. In this chart, as I conclude, there are illustrated all the parameters discussed in this lecture. The site specificity is very important. Minimum load transmission, and maximum biointegration. So we have 3 aspects to consider: the fixture geometry, macro and microstructure, the fixture abutment connection tapered, Platon switching concept, the surface characterization, micro, nano topography, and chemical composition. So you can obtain a less stress distribution, stress distribution, SOX absorption, and flexural strength. No microgap if you use a tapered connection with less of 10 microns of microgap. No bacterial infiltration. If you utilize a system with a macro-nano topography organization, you can have a faster cell adhesion, proliferation, and differentiation. And all these parameters lead to the 3-dimensional osseointegration, no micro-movement, no rotation. What means 3D osseointegration? When the bone grows on the shoulder of the implant. If you put the implants with a tapered connection under the level of the alveolar crest, you have the bone that grows over the shoulder. But if you have a conical connection and vertical interface, a tube-in-tube interface, you don't worry about it, because you don't have to remove the bone of the shoulder. You must can introduce the healing screw, and you have finished. You have a perfect adaptation, because the adaptation is not on the horizontal surface, but in the vertical surface. No micro movements, no rotation, reduced time of osseointegration, DSLI design, transmucosal connective tissue seal, long-term marginal bone level stability, and soft tissue stability. I would like to thank for your attention.